we recall, what we did last time in nutshell was a spring, well, a simple harmonic motion moving front and back, right?
Yes.
With your force was what? Kx with the negative, isn't it? And your force was mass times acceleration and minus kx. Basically, your acceleration was k over m, right? And if you use the uniform circular motion, x was a cosine of theta, which was omega t, right? And your acceleration was, if you do derivative twice, you will get minus and then omega square, and then it comes up to be cosine omega t, which turns out to be x. This is where we left last time. So when we compare this, right? So this will be, well, with minus, so this will be actually omega square equals to k over m, and this implies, well, omega is, this implies well, omega equals to square root of k by m, well, you can use plus minus also, and your time period is what? Omega was 2 pi f, basically it's 2 pi over t, and then your time period was 2 pi square root of m by k, right? That's where we left, and we did a couple of problems also. We did the energy, potential and kinetic energy, total energy. The graph was this. You still remember this, right? Right? This is from A plus A to minus A, right? At this point, your kinetic energy was maximum at the center, right? Potential energy is 0, elastic potential energy basically. And then what happens is, as you go away, your elastic potential energy keeps on increasing, becomes maximum, whereas at the end, your kinetic energy becomes 0, right? But your total energy at any point remains the same. And we did a few problems also in the last class. Now, this was about the horizontal thing. How about if we make a spring vertical? Alright, vertical spring. Alright, I have a spring, okay, and now what I do is I want to hang a certain mass here, so that what happens, it goes a little bit down, right? So I use another ink, let's say. So this is after I, okay, this is after I hang a mass, let's say it goes somewhere here, alright, it extends. This is my mass m. So if I have mass m, this mass acts the force vertically downward, isn't it? The force equals to mg, goes down, right? But since it is in equilibrium, the spring also exerts some force upward, right? What is the force that the spring apply upward? What is it? K times x, right? Well, it's negative, right? Negative of this. But now we take only magnitude for now. So let's say the spring also apply. This black is the spring force, okay? So the force will be k times x. By the way, x, no, let me take this length, not x, because this length, let me take something y, something different. Okay, so now I can tell this as ky. Okay, so now what I do is I want to lift this a little bit up. Alright, I apply a little bit force and lift it a little bit up. Now what happens, my third case, I use my blue ink. Oops. I use my blue ink and let me lift it a little bit up, so that now it squeezes a little bit, but not like earlier. Squeeze a little bit, oops, okay, something here. And then my mass is now up somewhere here, okay? And this displacement from here to this one, I lift it, oops, okay, I put it here, something called x. I lifted it up about x from the position what it was before, alright? So if I lift it up, now what happens, my downward force is same because my mass has not changed, isn't it? My mass is exactly the same. So my downward force, I can leave it like this. My downward force is exactly the same, which is mass times gravity, but my spring force will be less than what it was before, because earlier it is stressed a lot, isn't it? So my spring force is quite long, but now my spring force will be a little bit shorter than what it was here. So my spring force is, let's say, only this much, not like too big, okay? So this spring force now, my F will be what? This will be K times? What is the displacement now? Spring original is here, right? Which is Y minus X, isn't it? Only this much, right? The spring displacement is K Y minus X, is that right? Am I doing okay? Alright. So now in this particular case, what happens when I release this? What happens? What is my net force? If I remove my hand, this will win, right? Isn't it? Because upward force is less, downward force is more, right? So my force net, let me use what color? Okay, F net, right? Net force equals to, what is it?
K times Y minus
K
X.
times Y minus
Minus.
X
Minus the weight.
minus this weight, right? Which is mg. Very good. So if you multiply this, which is ky minus kx minus mg, is that right? So now what happens here? What is ky?
K
Right?
Y
This equals to mg, right? Let me write it down here before I forget. So in this particular case, your mg is equal to ky, isn't it? Right?
Okay.
Because it is
yeah.
in equilibrium condition at this point, right? So these two are the same thing. Well, one is up and the one is down. Actually, what happens here is this plus this total force is 0. Actually, mg minus, actually ky minus mg equals to 0. That's why ky equals to minus mg goes on the other side, becomes plus mg. Alright? But in any case, it's mg equals to ky. So what you do is you replace this ky with your mg. Now what happens there is, this will be what? This will be mass times gravity minus kx minus mass times gravity. This will cancel, and your F net is what? Minus k of x. Again, it is the same thing as here. Alright? So let me go change it here. Your force is what again? Mass times acceleration is negative of k of x, but or in other words, acceleration is negative of k over m of x. Your acceleration can, well, this is along x direction. Everything is along x direction, okay? X means y, by the way, here. Alright? The direction of x is what? Downward. Isn't it? So this x is downward. So this one means what? Negative of omega square x, right? This is from here. So again, if you compare this, omega square equals to, going back to the last class, right? This is from the last class, right? So going back here, your omega equals to again square root of k over m. So back to the same thing. Omega is 2 pi by t. Well, this is one thing. 2 pi by t square root of k over m. This implies your time period is, if you flip it, 2 pi goes on the right, and then this also gets flipped. Square root m over k. So this is the time period of the spring mass system vertically, right? Not like horizontal what we did last time, but even with the vertical also, it will move with the simple harmonic motion. So the problem is there's a card. Oops, I will draw the card. Okay, anyway, there's a card. Alright, there's a car, has a certain center of mass, whatever, right? And a person step here. The car initially is here, okay? Because of the weight, just like the spring mass system, right? It's right here, okay? The car has a shock up there. It hits a spring, whatever, because the spring is here, alright? So now what the question says is, if a person of, let's say, 100 Newton, alright, 100 Newton is only 10 kilogram, right? Oh, that doesn't make sense. Or maybe 100 kilogram. So 100 kilogram person, right? 100 kilogram, oh, that's a heavy person. Right? 100 kilogram is almost 200 something pounds. That's okay. That's okay. 100 kilogram is almost 1,000.
That's the average of the US.
Almost 1,000 newtons. What is it? Anyway, point here is whatever mass, additional mass, when you add it here, alright? When you add additional mass there, it means now that additional mass will suck up this a little bit displacement here, alright? So that will be your x, a little bit displacement.
Yeah.
So whatever is the x is given there. That will help you to find k. Why? Because your F equals to kx, right?
K equal to F of X.
So F is whatever Newton, additional Newton, because that additional mass had made this displacement, isn't it? Not the car mass. Are you following? So the additional mass, this will help you find k, because if you need to find the time period of this oscillation, what you need is you need m and k, isn't it? So all you need k, you get it from here, right? You have the mass there, that mass is defined as k. So you need this extra thing to get n k, and once you get n k, just plug it here and get your time period. So that is one of the problem. Okay, I'm not going to do in detail, but this much hint should be enough for you to do that problem. All right? Torsional pendulum. I call it pendulum. It's actually, what does it mean is, have you seen the mechanical watch, the old type of watch inside it? All right? Right? Yeah, right? You know that. So what happens there basically is you have the fixed support there, and there's a spring, right? The spring not like this spring, but well, in this spring also, rather than pulling it down, what you do is you rotate this spring, let's say. Okay? Now what happens this spring is it goes this and this, right? Right? So that is also a simple harmonic motion. Are you following? That also goes like up and down if your theta is small. Let's see what happens there. So the spring is, how do I draw? This spring is like this. Oops. Right? So initially, let's say this position was here. Oh, let me make it down. Oops, I erased all of them. So let me say, well, I'm making a mess here. But I hope you'll understand this. So what I do now is, I apply a small amount of force here on this side, so that this will displace here. Right? So now what happens if this position displaces here, now it tries to go back, right? Oops, here, let's say. This one, if you move it here, and it goes back here again, isn't it? So it keeps on swinging from here to there. This is your initial position. Right? Since you are using the force in the perpendicular direction of with the radius, isn't it? We call it something like a wrench. You have a wrench here. You try to open, you torque. Yes, there you go. You apply a torque there, isn't it? So torque is basically call it tau. All right, tau is proportional to theta, isn't it? This is theta, this angle. More torque, more will be theta, isn't it? Right? So basically tau, if you use equal, you have to have one constant. Now it's called kappa. It's just like k. F equals to k. Just like similar to this. Where is it? Oh, it is there anyway, right? Right? So now this was the linear thing. Your linear displacement is your linear force, isn't it? Now if you have torque, more torque will create more angle. Angle is proportional to the torque applied, so minus, and it will be negative because the torque applied by your torque applied, when you apply on this side, the spring will apply on the opposite direction, right? So this torque is the torque applied by the spring against you. Numeric magnitude will be same, but this will be minus kappa times theta. Is that right? Similar to this, right? And this is also called what? The torque is also called what? Torque is like force, isn't it? Force is what? Mass times acceleration. So in case of torque, mass corresponds to what? Mass corresponds to what? Moment of inertia, yes. Mass corresponds to I, and acceleration corresponds to what? Alpha. Very good. Acceleration corresponds to alpha, right? So when you equate this, same thing, just like this. Mass is I, alpha equals to kappa theta, right? So now what it means here is I alpha equals to minus kappa theta. So your alpha equals to minus kappa over I times theta. Is that right? Is that right? So if you do the same thing, this alpha is what? Second derivative of theta, isn't it? This one is second derivative of theta dt square, isn't it? Right? So if you compare with the relation with what? Omega square, isn't it? So this guy will be omega square, isn't it? Right? So if you compare with d square theta by dt square, which is minus omega square theta, if you do the same thing, isn't it? Theta equals to theta 0, whatever. Theta equals to, you have like theta 0, alright, or the amplitude, right? And then cosine of omega t or something, isn't it? Right? And you do the derivative twice, you'll get this. It's the same like before, isn't it? So this is your acceleration again. Actually, this acceleration is along z direction because your acceleration, oops, it's alpha, isn't it? Alpha, because you are doing with theta, right? This is along the z direction because you know this thing, right? Isn't it? Right? So now when you compare this thing, what happens here is your omega square equals to kappa over moment of inertia, or omega equals to square root of kappa over moment of inertia. So which implies omega is what? Omega is 2 pi by t, isn't it? So this will be 2 pi over t equals to square root of kappa over I. So this implies your time period is 2 pi square root of I over kappa. So when you compare this, basically the time period of this guy, isn't it? If you look at this one, it is pretty much same. The difference here is what? M is replaced by moment of inertia, isn't it? K is replaced by kappa. Make sense? That kappa is called torsional constant. By the way, this guy is called torsional constant. Just like the force constant here. This was force constant, isn't it? Right? Now we have torsional constant. So basically, your spring, if you rotate it rather than pulling it, you just twist it, then that also executes the simple harmonic motion. Alright? Where the time period is given by kappa over moment of inertia. Since it is like rotational case, now that has to do with the moment of inertia, not the mass. Alright? It has to do with the moment of inertia. We discussed the moment of inertia already anyway. I displaced it a little bit. Alright? So let me put the mass here. If I displace a little bit, only remember that small angle in the last class, small angle was very important because remember, simple harmonic motion, it has to be like in a straight line, isn't it? Simple harmonic motion is the projection of a circular motion in a straight line, isn't it? Right? Our grandma sewing machine, right, was what? Grandma pedal was simple harmonic motion because it just goes up and down, and here it was circular motion, isn't it? Make sure the simple harmonic motion means it has to be a straight line. So this pendulum, you are hanging a certain mass, right? If you hang a certain mass, as long as small angle, then only it is approximately straight, right? Just like the spring attached with the mass moves straight front and back, isn't it? The pendulum also, as long as small angle, it is almost straight line. As long as the angle is small, then only it will be a simple harmonic motion. Are you following? If it's big, then it will be like a circular motion, kind of. Are you following? So when you have, let's say, small mass here, so this goes here, this mass goes here, all right, making an angle theta with the vertical. Now what happens here? This force vertically downward will be mass times gravity, right? Is that right? So mass times gravity will be vertically downward. What will be this component of the mass? I keep on switching this mass here and there, so let me put it here. Alright? What will be this component of mass? The force. What will be this side force? If this is your theta, this will be your theta, right? Right? Look, this is theta, right? isn't it? Now, what will be this component? Sine, right? Very good. So this component will be what? Mass times gravity times sine of theta. Is that right? So this mass times gravity times sine of theta will lead me to what? My force on this side will be mass times gravity times sine theta. Is that right? But my theta is very small. My theta is small. If my theta is small, theta equals to what? This is your displacement, right? Right? The displacement is, let's say this is my x. Are you guys with me? So if my displacement is x, what will be my theta? In terms of x and L.
Really small.
If it's small, okay. Alright, so I can just replace this sine theta is theta, right? Because my theta is very small. So if angle is small, sine theta is approximately equal to theta. And your theta equals to what? L by R. Right? Theta equals to L by R, which is x by L. So basically your force equals to mass times gravity times x over L. Are you getting that? Right? Mass times gravity times x over L. Or you can also say this way. You can also do this way. If theta is very small, alright? If theta is very small, this can be considered as hypotenuse in this small right angle. Are you following? Or this can be hypotenuse or this can be hypotenuse. These are the same thing anyway, isn't it? Right? So because this is so small, both are hypotenuse. This is your perpendicular, right? So sine theta is what? Perpendicular by hypotenuse. Isn't it? X by L. Did you get that? Right? So you can take it that way also. If you don't understand this one, you can consider that since it's so small, you can take this as a hypotenuse, or this one as a hypotenuse. So basically, perpendicular by hypotenuse, right? So this x will be perpendicular almost, because it's so small. It's perpendicular to this or perpendicular to this, right? But this is pretty obvious. In your calculator, what you do is make sure you use your theta and radians. All right, make sure theta and radians and put very small angle, 0.0 something, right? And press sine. Use the sine, you'll get the same number. Try it. All right. So anyway, so once you are here, now what happens? Your force is what? Mass times. Force is mass times acceleration along x. Is that right? So this will give me what? Mass times gx over L. Mass will cancel. Your acceleration ax is what? G over L times x. Is that right? Oh, by the way, I forgot one thing. Your force is against x, so basically it is negative. I forgot to put negative there. Isn't it? Because I said x is on this side. This is my origin. My force is going this way. Force is opposite to the displacement. So I have to use negative sign there. Isn't it? Now, now comparing it with what? This expression. Where is it? This is what? This is the expression for what? But what is ax? Is minus omega square x? Is that right? If you do it derivative twice, you know, isn't it? A cosine theta, and when you compare with this, you'll get yes.
In that case, where the mass of AX equals negative m gravity of x over L, will we ever get a negative force and then also on the other side a negative? So
No, your force equals to negative. That's why your acceleration comes out to be negative. I know what you mean. So you are putting this also minus and this also minus. No, this is relative term. X and f are the relative term. If wherever you have chosen the direction of x, your f will be opposite of that. That's why you have to have one side. This is minus, then you have to put minus.
So it
then
always
will
has
be
to
plus.
be opposite.
You cannot put minus here, and then it means both are on the same direction.
Okay. Alright.
Okay, so now what it means? What it means is omega square equals to this guy, right? Square root of, is that right? So what it means is, omega square is this one, and then omega equals to square root of g by L. So what it means is 2 pi by t equals to square root of g by L, or time period equals to, you flip it, 2 pi goes there, and square root L by g. So this is what we did last time in the lab, isn't it? Right? So the interesting thing here is, what you notice here is you don't have mass here in your expression, isn't it? So what it means is, no matter whatever big mass you put there, no matter what mass you put there, your time period will not change. Are you following? And as long as, remember, it does not depend on theta or x also. As long as your displacement is small, within that range, isn't it? It doesn't really depend on your displacement also. Are you following? As long as small angle, about approximately 4 degree or less. Alright, depending on your length of the pendulum. Alright? Now one additional thing. What is the length of a seconds pendulum? The bob is there hanging with a massless string. In that case, your string is massless, so whatever mass you hang there, as long as it is a point mass, kind of a, it counts as a point mass. Alright? It does not depend, your time period does not depend on the mass. That's what we did in the lab also. We changed the mass, isn't it? We put 200, still the time period was same. 100, and then you put 200, time period didn't change, isn't it? So now the question here is, in the seconds pendulum means where the time period is 1 second. So when it goes here, 1, 2, time period means what? When it goes there and comes back to the same position, isn't it? That is what we call time period. 1 second, 2 second, 3 second, right? So if you have a massless string and hang a mass there, to make a seconds pendulum, your length is fixed for the given acceleration due to gravity, because this is constant, right? Isn't it? This is constant, 2 pi is constant. So use t equals to 1 second, alright, and find L from this equation. That will be the length of the seconds pendulum. Are you following? Alright? Do it yourself. That's your homework. Remember, I erased this one, the pendulum thing. I still have this. Alright? Because the next one we are going to do is pretty much similar to what we did in the torsional. Okay? Here, the physical pendulum is a pendulum, with a mass something weird, and hanging it here. Alright? So when it swings, remember, this pendulum was what? This pendulum was like a mass and a ball, isn't it? Right? But you have like a weird shape. Now what happens is, it has a center of gravity somewhere here. Center of gravity we did last time, right? So this one is center of gravity. What we did is, if you apply a certain force, now this will apply force back. So what happens is, this will move a little bit. Let me use a different color. Initially it was like this, alright? Initially this was from here to here. The distance from this fixed position to the center of gravity, I call it D. Alright? I call it D. D is the distance to center of gravity. Alright? Does it look like D? Okay. So now what we did was, this moved a little bit. Now this also swings like a pendulum, isn't it? But this is different than the simple pendulum. Alright? Simple pendulum was almost in a straight line and a single mass, point mass, isn't it? because the string was massless. Now if the string has a certain mass, now it comes something like a torque now. Why? Because when you move a little bit, let's say this will be
That's right.
this will be something like this, right? Can you see that green one? So your center of mass moves here, isn't it? And then this one, this is my D. The same thing, D displaces this much, right? So here, at this point, my weight was mg on this side, isn't it? When it goes here, my mg will be same down, isn't it? Right? My mg will be same down. Let me not write this because this will confuse you. So my mg will be same down. This is my mg. So what force will be, if this is your theta, if this angle is theta, then what force will be on this side? Same like before. What force will be here? mg sine theta, same thing, isn't it? So this one will be mg sine theta. Is that right? Because this is my theta, this will be theta, isn't it? So the adjacent side will be mg cosine theta, so this part will be cosine theta, and this part will be mg sine theta. So mg sine theta will be the force that brings me back. But here's the problem. The mass is not only this, the mass is the whole mass, isn't it? You cannot use simply force equals to kx, isn't it? Now you have to come back to where? Something called torque, right? Now the torque is what? Torque is force times perpendicular distance, isn't it? Right? Do you still remember that? So my force, which is negative by the way, because your displaced angle is there, so negative, your force will be mg of sine theta, is that right? This is your force, and what is your radius? What is it? When it rotates, radius is d, very good, right? D, isn't it? You have your d there, you apply a force. Actually, when you displace it, actually the force will be applied in the negative direction, isn't it? Of the displacement. Are you following? Negative direction of theta. You increase theta means your force will be this way. Your torque will be applied in the opposite direction by the system, isn't it? Due to the gravity. So now, this will be the force times distance, this will be the net torque. Alright? So now what it means is same thing. Sine theta, small angle. So that torque will give you minus mg, and then I put it d there, and then I put here theta. Right? Are you guys with me so far? Right? So now what happens? Now what happens? Here, but my torque is what? Right? Isn't it? And my torque is, where is it? My alpha is this guy, right? Right? So my torque is this, so torque is I times alpha, isn't it? Right? Torque is I times alpha equals to minus mgd of theta. By the way, theta is small. Theta is small. So then only sine theta can be replaced by theta, isn't it? So now what happens here is I alpha is this. Your alpha is minus mgd divided by I of theta. But when you compare with this equation, remember I did not erase yet. Right? Which is basically this, isn't it? If A is omega square x, your alpha is minus omega square theta, isn't it? So if you compare with this equation, comparing with, now I can remove this one. So if I compare with alpha equals to minus omega square theta, which is basically, this is the second derivative, right? I don't need to do that again. second derivative of theta, which is theta equals to some theta 0, some amplitude times cosine of omega t thing, right? So now what happened here is omega square equals to, what is it? This guy, m g d divided by I. So this is what? Omega equals to square root of mgd divided by I, which means 2 pi by time period is square root of mgd divided by I. This implies my time period equals to 2 pi, this gets flipped, I divided by mgd. So this is the time period of a physical pendulum. When I say physical pendulum, it is a bulk thing. Bulk thing means it must have moment of inertia about that particular point where it rotates, isn't it? So it has to have the moment of inertia. Mass only will not solve like your pendulum, simple pendulum. All right, since this has the mass here, isn't it? But mass plus about what is your center of gravity, and that center of gravity, how far is the center of gravity from the axis of rotation? All right, so that it swings, axis of swing. So you need to have your I also, you have mass also, and you need to have gravity, and then the distance of center of mass from the point of rotation when it is hanged there. Let's do one simple example. Just like, by the way, just like simple pendulum, we did this. Right? I may ask you another simple thing also in simple pendulum, where if the length of the string is, let's say, 1 meter, right? And Bob has a certain mass, let's say 2 kilogram. By the way, that you don't even need, but I may confuse you. So, well, not confuse you, but I may give you in your question, but you immediately know that math has nothing to do in case of simple pendulum, isn't it? Even if I give you 2 kilogram, don't wonder like, I don't know, where to try to figure out what formula where it has mass, right? And then you keep on screwing up the problem, right? Okay, yes.
If I gave you the displacement of the spring and the mass, you calculated the spring constant.
If you give the displacement
Yeah.
and the mass hanging there,
Correct.
of course.
Could you make an example?
That's what we did earlier.
With actual numbers.
Right. So you have a mass, that mass you multiply by gravity, that will be your force.
Divided by this.
And you have the displacement, right? You said.
Yeah.
So when you don't put the mass, you have like somewhere there. After when you put that mass, it extends certain distance, right? So that means your mg equals to kx.
Yeah.
So k equals to mg by x. It's pretty simple,
Okay.
right? Okay. Any more question? Okay, so in this problem, if I give you the length and the mass and when, and if I ask you time, by the way, if I ask you to calculate frequency, what do you do? If I ask you to calculate frequency, f, 1 over t, isn't it? You will get time period and then get, divide by,
That's
right?
the inverse of that.
Inverse of, yes. Or actually there's a formula which is inverse of square root of this, where is it? L by z, that will be g by L, 1 over 2 pi g by L, okay, square root, which is basically inverse. So anyway, don't go that route, just use this. Okay? If I ask you to find the angular frequency omega, what about angular frequency? Angular frequency. This is omega, right? Omega equals to 2 pi f. Omega over, well, yes, well, f equals to omega over 2 pi, so on. Anyway, so what about if I ask you length, well, whatever if I ask you, well, it has nothing to do with the amplitude, because in case of a simple pendulum, it is not dependent on amplitude, isn't it? In a formula, you don't have A. All right? So well, there are several other things which you may be able to do it. But now what I'm doing here is, okay, if I have, now what I do is, I have a rod. All right? A block, a rod of, let's say, 1 meter. All right? hung at one end. By the way, this is at one end, okay? Let me make it one end. Alright? And now if I displace it a little bit, what will be my time period? You know, this is a problem. So find time period in this case. My rod has a mass, it has a mass of, give me a number, let's say 2 kilogram, right? Use anything. You have 2 kilogram mass hanging here, 1 meter, the length is 1 meter long, alright? And the mass is 2 kilogram. And if you swing a little bit, small angle, what will be the time period? How long it takes to go there and come back to the same position? How will you do it? Remember, your formula is this. Is everything there? What is D? Well, you need I. First, you need to find out what? Your formula is pretty simple, 2 pi, your formula is I, because this is what? This is not the case of simple pendulum, isn't it? It is the case of physical pendulum. Because your mass is distributed all around, isn't it? Now, this is a rod, a uniform rod. What that will help you is to find the moment of inertia, right? So, moment of inertia, what will be? Well, the formula will be mgd. So, if I have this shape, where will be your center of gravity? Halfway through. So, your center of gravity will be here, isn't it? So, your d will be what? Half a meter. So, your d equals to, very good, 0.5 meter, because d will be from here to there, right? So you have one thing, you got this one, you know this guy, right? You know this g. Mass is also given. The problem is here, right? And this you don't need to memorize. I'll give you formula sheet. All right? Yes. The formula sheet, the formula for this one will be 1/3 of ml square. All right? So from here, what you do is, first of all, you get I. Use 1/3 of mass times length square, right? Sorry, 1/3, not 1/2. It will be 1/3. By the way, if it was at the middle, and if you rotate like, by the way, it will spin, right? Isn't it? It will not swing if it's at the center. But in that case, the moment of inertia would have been 1/12 of. All right? But since at one end, your L is this much, the whole L, so this is 1/3 of ml square. All right? That's the moment of inertia of this case. Again, I'll give you this formula. Okay? You don't need to panic. Don't want you to derive. All right? So if I give you like this, or if I give you a rectangle block, or if I give you like circular thing, you know, like a circle, and then you hang it from here, and then you swing it, isn't it? Whatever shape I give you, either I give you the moment of inertia, or I give you the formula to find the moment of inertia in that particular shape with that pivot there. Are you following? So the point here is, you have to do an extra work to find I, right? Once you get I, so just do it for me. Your mass is what? 2. L is what? L is 1. 1 is square. Oh, I don't need your help. It's simply 2/3. Alright? Is that right? So now you get, let me go here. So your time period is, just you calculate yourself, 2 pi square root. So this will be 2/3, and your mass is 2 times gravity is 9.8 times your d is what? 0.5. Let's calculate this quickly and then give the number for me. So this will be whatever second. Can you quickly do this? What is it? Anyway, you know how to do it, right? So these problems are pretty simple problems, all right? So pretty straightforward problems.
1.64.
Say it again.
1.64.
1.64. Is it that big? 1.64 second. Okay, could be. Yeah, almost 1.5, right?
Yes.
1 second something. Okay, I trust you.